Thank you so much, ma'am. Thank you so much, sir. Good morning to one and all present here. Coming together is a beginning. Keeping together is a progress. And working together is a success. With this beautiful quote, I, Neha Joshi, is pleased to welcome all honorable guests, all dignitaries and participants in second technical session of 3-day International Conference on Physics at the World Contemporary and Innovative Application, jointly organized by Department of Physics, Christian Eminent College, Indore, and Research Foundation of India, in association with IAPT, Indian Association of Physics Teacher, and supported by Dr. Shyama Prasad Mukherjee University, Jharkhand, sponsored by WFST, World Federation of Science and Technology. Yesterday, we have successfully completed our first technical session, and today is the second technical session of 3 days international conference. Our technical session chair, respected Dr. Neeru Bhagat Madam and respected Dr. Uttam Sharma Sir, are among us. I extend a warm welcome to our session chair, respected Dr. Neeru Bhagat Ma'am, Associate Professor Physics, Symbiosis Institute of Technology, Pune. BSc and MSc in Physics, Dr. Neeru Bhagat Ma'am obtained her PhD degree in Physics Material Science in 1999 from Inter-University Consortium, Devi Ahia University, Indore, Madhya Pradesh. Ma'am started her journey with work as a senior research fellow at National Environmental Engineering Research Institute, NIRI, Nagpur, India, and got research associateship under National Council of Scientific and Industrial Research Fellowship at Nagpur University, India, on nanocrystalline alloys. It is my immense pleasure to say that ma'am also worked as BITS Pilani, Dubai campus, International Academic City, as assistant professor in 2002-2008 and become associate professor in 2008. In 2013, ma'am joined Symbiosis Institute of Technology, Pune. Dr. Bhagat ma'am has more than 22 years of academic experience and research experience too. More than 15 research papers are published in national and international reputed journals. Dr. Neeru Bhagat ma'am attended numerous national and international conferences and delivered many invited talks. Ma'am supervised 4 MSc projects and 4 PhD students are taking benefits of her supervision. Her research interests are mechanical, structural, and magnetic properties of nanocrystalline and amorphous metallic classes, improvement in tissue growth and antitoxic properties of silver and gold nanoparticles by modifying the synthesis process, and exploring spin reordering in magnetic and non-magnetic thin film by changing interface roughness. Ma'am completed 2 research projects funded by UGC DEE CSR Indore, India. We are really blessed to have such an eminent personality as our session chair, and we extend warm welcome to you, ma'am. Welcome, ma'am. I also extend a warm welcome to our second session chair, respected Dr. Uttam Sharma Sir, Professor and Head, Department of Physics, Shri Vaishnav Institute of Science, Shri Vaishnav Vidyapit Vishwavidyalaya, Indore. Sir, awarded with PhD in High Pressure Structural Phase Transition from School of Physics, Devi Ahilya University, Indore. It is my honor to say that Dr. Uttam Sharma Sir is an Honorable Secretary of IAPT, Indian Association of Physics Teacher of MP Region. Sir is working as a coordinator at Center of Excellence in Plasma Research at Shri Vaishnav Vidyapit Vishwavidyalaya, Indore. Sir is having huge 26 years of teaching experience. Dr. Sharma is working as a principal investigator in 2 research projects and completed 3 research projects. Total research grant 127 lakhs with funding agencies like MPCST, BRFST, BRNS, and GSI, etc.
Neha madam, sorry to interrupt you. You
Yes,
introduced,
sir.
you already introduced myself yesterday itself. So I think,
Yes. So
thank you
today
very
we
much.
have new participants are there. So
No,
I
no, no,
want
no.
to.
I think this much is enough. Thank you.
Oh, okay, thank you so much, sir. It
Okay.
is a matter of great pleasure and honor that such an eminent personality is here among us, and we extend our warm welcome to you, sir.
Thank you, madam. Thank you.
I will not take more time.
Hello.
With the
Hello.
permission of our session chair, let's start our second technical session of 3 days international conference on physics at the World Contemporary and Innovative Applications. First of all, I would like to instruct all participants. All the participants are requested to mute their mic until they are invited. Each participation will be given 7 minutes for presentation and next 3 minutes for the question answer. In case any technical error occurs during presentation, participants will be invited later on. These are the instructions. Please do follow. Ma'am, sir, shall we start our... Yes, ma'am.
Miss Neha, I think somebody has raised a hand. You can just look at that.
Yes, ma'am. I will check. I think... मैम शायद उन्होंने अपना रेज हैंड डिक्लाइन कर दिया है सो वी विल कंटिन्यू विद आवर फर्स्ट पार्टिसिपेंट थैंक यू सो मच मैम I would like to call our first participant for the paper presentation, respected Nischal Yadav, sir, at PS Malviya, respected Manpreet Kaur, and respected CS Sharma ji, combinedly presenting their paper. Is my voice audible? Nischal Yadav, sir, PS Malviya ji, Manpreet Kaur ji, CS Sharma ji. Are you getting my voice? Ajay, sir? Ajay, sir? I think they are not in meeting. So we will call our second participant for the paper presentation. Dr. Sunil Khatri sir and P.A. Kakre sir. Ma'am and sir, Sunil Khatri sir will present our his second paper presentation. Dr. Sunil Khatri
Okay, madam.
sir.
Okay, madam.
Yes, sir.
Okay, madam. Yes. Okay, madam. Yes, madam. Start. Are you audible
Yes,
to me?
yes, sir. Yes, sir. Yes, sir. You can start.
Yes.
Yes, sir.
So today we have present respected dignitaries. Today we have present my research paper, X-ray absorption fine structure studies of some copper dithiocarboamide complexes, and along with me there is a Dr. Praveen Kekre, which is professor of PMB Gujarati Science College as well as head. So introduction. In the recent year, EXAFS technique has been developed as a powerful tool for investigation of the geometrical structure of polyatomic, amorphous, and complexes in solid as well as in liquid state. The aim of the present study is to measure the X-ray absorption spectra of 3 copper complexes, which are mentioned over here. And such a study provide useful information on the fine structure of the K absorption of the copper 2 complexes. We have derived the phase parameter alpha 1 beta 1 corresponding to the first coordination cell in the present investigation. Experimental details: a Sept shell X-ray tube with tungsten target operating at 16 kilovolt and 60 milliampere was used to the source of continuous radiation, and 0.4 meter Kochis type band crystal transmission spectrograph in its improved form has been used to record the spectra of the complexes. The result and discussion: the profile of the K absorption discontinuity of 3 copper complexes are shown in figure 1. These are the absorption versus energy graph of 3 complexes. The exhaust of copper complexes are interpreted in terms of graphical method proposed by Lattice. Just a minute. Proposed by Lattice. The value of wave vector K were obtained from the equation K equal to 0.263 e to the power 1 by 2. So where E is the energy in electron volt of the peak in the exhaust measurement for the age, the K value thus obtained are given in table 1. The value of K of major peaks of exhaust spectra are reported in table 1 for the copper complexes. The N versus K plot for copper complexes are shown in figure 2A, 2B, and 2C. These are the N versus K plot for the different complexes. And from this, we calculate the value of beta 1 and taken alpha 1 from the references given by Lattice, because value of alpha 1 is same for the all the complexes, which is reported in table 2. So this is the equation number 2. With the help of equation number 2, we can determine the value of bond length, which is reported in table 2. So table 2, the value of the bond length is reported for 3 complexes, and value of beta 1, which is 3.2, 2.8, 2.9, corresponding to the complexes which is shown in the table, and alpha 1 value taken as same, because our in the 3 cases the value of the central atom is copper, therefore here we take an alpha value will be the same. But due to the variation in ligand, the beta there is a variation in also in backscattering phase. Beta 1 is different for the different complexes. Alpha 1 taken from the references. Okay. The number of attempts has been made to determine the phase shift theoretically. According to Teo and Lee, the total phase shift expressed by the ejected photoelectron is given by Teo Lee phi AB equal to phi A plus phi B of K minus pi, where pi B is the phase of the backscattering amplitude from the neighboring, and phi A is the phase shift due to the central atom. The value of delta, when plotted, the value of delta is calculated from this equation. This is the equation. We substitute over value of alpha 1 and beta, and we will get the value of delta for all 3 complexes. Fine. And we plot the delta versus K from this total phase shift versus K plot, which is the straight line. One may expect that the total phase shift for all complexes belong to a given system should be the same. However, this is not in the case. We find in figure 3 that delta 1 versus K plot are different for different complexes. This may attribute to the change in the ligand. Conclusion: in the present work, it has been observed that the graphical method of Lytle, when applied correctly and carefully, can give useful information about the bond length, total phase shift. This method is simple and straightforward and provides a physical picture of X-ray absorption process in studying the system such as amorphous material, etc. These are the references. These are the references. Thank you very much.
Thank you, sir. Neeru ma'am, Uttam sir.
Thank you so much, Dr. Sunil. Quite an interesting
Thank you, madam.
study. Just a few suggestions I have. It would actually raise the standard of the presentation as well as the conference if you actually use a PPT for presenting instead of a paper. So, kind request that you can keep that in mind. Another thing, have you tried to get the same result or compare the result with theoretical calculations?
No, it is not. It is compared the result given by TU and LEO.
Yes, yes.
Whose results are more or less a straight line, and our result will also be same, the straight line.
Yeah, what I'm
not
trying
calculate the theoretical.
what I'm trying to say is because the current trend is that all these, especially if you take up new systems like different combinations which have yet not been studied, you can use machine learning to get the proposed changes that would be, and then you can check it with the experimental data. So that is something you can probably think of doing. So that will probably enhance the work. That's all that I have. Thank you so much.
Okay, madam. Thank you.
Thank you, ma'am. Uttam sir.
No thanks, no question. Nice to see you, Dr. Khatri.
Thank you, sir. Thank you, sir. Dr. Sharma, sir. Thank you. Thank you very much, sir.
Thank you so much, sir. Thank you so much, ma'am. Now, I would like to call our next participant for paper presentation, respected A. Rajeshri and G.S. Kumarji and P. Manoharji are combinedly presenting their paper.
Mr. Madam, namaste one and all. Yeah. A very good morning to one and all. Within a few seconds, I'll start my presentation.
Yes, ma'am. Yes, ma'am.
Yeah. Welcome to this first international conference on physics at World by this Christian Eminent College, Indian Association of Physics Teachers, Research Foundation of India. My topic is
Hello.
there is
Ma'am, your mic
problem. Yeah. Mic.
Yes, ma'am. Yes, ma'am.
Mic.
Yes, ma'am. Your voice is audible now. Now.
Thank you. Voice is audible. There is some net problem. Please wait.
Yes, ma'am.
Yeah, my topic is actually it is related to theoretical physics, madam. Physics. So the topic is study of refractive index profile near the surface of YVO4 waveguide using point dipole approach. So our subject is research subject is related to point dipole approach, theoretical approach, of course, and yeah. YVO for yttrium orthovanadate. So first of all, let us see its properties. Actually, it is a positive uniaxial crystal having a positive itself means Ne, the extraordinary ray refract is greater than ordinary ray refractive index, that is Ne is greater than No, and it has got tetragonal structure and A, B, C values are given, and of course Ne, No values are also noted here. So its main characteristic or importance of this bipolar property is it's large birefringence. It is the main property of this YbO4. So that is also noted here. At particular given wavelength, that is 633 nanometers. And other properties are, it has got high conductivity, good mechanical properties, and good chemical stability. And then here, what we have calculated is the refractive index calculations using this point dipole approach. And actually what is happening here, the main point is, these optical waveguides, or since they are becoming increasingly thin, surface variations and near surface variations of refractive indices would have to be considered for evaluation of propagation parameters in such devices. That is, if you see the refractive index on the surface of the waveguide or this thin film, and if you see this refractive index somewhat deeper or interior of the thin film or waveguide, both are varying. There is a change. You can find the change in the refractive indices when you see it on the, or when you calculate them on the surface of the waveguide or in the interior of the waveguide. So that is the main point, and that made us to calculate or to work on this topic. And of course, next thing is, as we proceed, the refractive index of any material is a function of the local field experienced by the constituent ions. This is the basic of this. And of course, we have got a lot of expressions behind this. So this is the conclusion part. Actually, how do we get the refractive index using point dipole approach? There is a lot of derivation is there. Of course, you use, all of you know, Clausius-Mossetti relation. So we make use of that expression, and finally we arrive at this conclusion for expressions nx, ny, and nz. And of course, it is missing, but ny is also, it should be there. I'm sorry. And of course, sigma dij, they are called lattice anisotropic factor. That is, what is lattice anisotropic factor? Here we are saying that the ion on the surface of the thin film or waveguide, it sees different environment, whereas the ion in the interior of the waveguide sees different environment. So this means, causes the geometric anisotropy. This is, so we calculate that using Ds. This is dxi. So this has an expression for this. And this case, this is the 4 pi by 3, this value. And of course, they have, this is a very famous, and this is a fundamental of this for this topic for us. This crystal axis and the Cartesian axis. So this is the how the crystal axis is related to the Cartesian axis, and what is the configuration it is named as, and how do you name the NENOs. So this SA axis, if it is parallel to X axis, so your NX will be NE, extraordinary ray refractive index, and NY and Z will be NO. So the configuration, it is named as Y cut X propagation, and if it is Z cut, it is X propagation. Similarly for Y axis, so Y means NY is extraordinary, other two are ordinary, and X cut Y propagation, Z cut Y propagation. Similarly for Z axis, here we have taken Z, okay, that we'll see later. The lattice anisotropy factors we have calculated using point dipole approach within the core. This is only core. Actually, we have the other part also on the surface. As you move from the surface to the interior, that is seen somewhat later. So first, let us see the lattice anisotropy factors well within the core. So at this particular wavelength, 6328 angstrom units, and of course, how we have calculated is it is like effect on one atom on other three. So Yi on Yi, Yn, Yj, Yi and yttrium on oxygen, like that, and then effect due to vanadium on yttrium effect due to vanadium on vanadium, effect due to vanadium on yttrium. So each point, like we have calculated all those things, and this is the interior, internal anisotropic factors of the given waveguide. So these are only these things we have got through some like C++ programming we have done. So making use of those, I've shown you NX, NY expressions we have already previously seen. So making use of those expressions, and with the help of C++ programming, we have got these calculations. These are the electronic polarizability values fixed alpha, Y, vanadium, yttrium, and oxygen, and calculated refractive index NX, NY, NZ, calculated and experimental. So this is the main thing. After calculating refractive indices, we go for birefringence. So that is the difference of these two, Ne and No. So calculated and experimental. So this is a very good approach, point dipole approximation. We are getting perfectly equal experimental and calculated values. And last we'll see the YVO for applications. Actually, all of you know that it's the oldest material used for laser host material, that is doped with neodymium, NdYVO4. And then it is used as a polarizer, optical isolator, beam displacers, and of course when you dope it with U+3, this acts as highly efficient red emitting phosphor, which is used in color television. And here we see the refractive indices like NO, NE, both of them. So red pointed graph is Ne and NO. So how the calculations, how we are getting the calculations, if we just see them, the NO ordinary values, this is on the x-axis distance, that is from surface to the interior of the thin film, and on the y-axis we have NO and Ne. So as we move into the interior of the waveguide, the NO, that is ordinary refractive index, it's going on decreasing, whereas extraordinary is going on increasing. This is for X-cut Z propagation. And of course here the how we have calculated, how we have moved from surface to the depth of the thin film or waveguide is, initially we have calculated the first point on the surface. So we set it as 0th unit cell, and then first unit cell. We have taken the third C parameter, third one, and third unit cell. What is the depth? So see 6.028 angstrom is below the surface of the waveguide. Then 2 unit cells, 2C times next further interior to the unit cell. Like that we have then on increasing the unit cell number, and when it is reached 10 unit cells, so we can observe that it is as well into the interior of the waveguide. So that is how for different C values we have calculated the ordinary ray refractive index and extraordinary ray refractive index, and we could calculate the birefringence, and we can see the graph that as we move into the interior of the waveguide, the birefringence, it is increasing. This is for X-cut Z propagation. Similarly, we have done it for Z-cut X propagation. Here the opposite thing is taking place. The Ne is decreasing, whereas No is increasing, and these are the values, so NO and Ne for the second case. And of course here the DN, that is birefringence, is decreasing here in this case. So we can observe this from calculated data. This is the conclusion. So whatever are the points we have calculated is a summary. X-cut Z propagation and Z-cut NO is 2.35. So it is that's what we have seen in the graph also. NO is decreasing, Ne is increasing for the first case. For Z-cut case, the NO is increasing and Ne is decreasing. That is the opposite. So one is the opposite. One is opposite to the other. The properties are different, opposite to each other. So what is the reason for this? The opposite behavior in the variation of NO and NE on and near the surface of the X-cut Z propagation, one case, and Z-cut X propagation is the other case, waveguides. Is primarily the reason is due to different dipole orientation for two distributions in the lattice, and also difference in directions of the electric vectors of light. So we have taken different directions, of course, X-cut and Z-cut. Propagation is also through Z propagation and other is X propagation. The directions are different, and owing to this, we find a different dipole orientation. So this is the reason for getting the values quite opposite to each other. Thank you very much.
Thank you, ma'am. Neeru, ma'am.
Thank you so much, Dr. Rajashree. That was quite an interesting study. Actually, I really found it very with par with whatever we need to do, because we are going thinner and thinner on our surface coverings and other things. So it's important to study these kind of changes in the refractive index. Thank you for this good work, and plus an extensive work, because you've done experimental as well as theoretical.
It is only theoretical calculation, madam.
Yeah, but you have compared it with the experimental.
Yes, madam.
That comparison is good.
Thank you very much, madam.
I think there was someone else who had raised their hand to ask a question.
Yeah. May I know?
Chinay sir? Yes, you may ask your question. Chinay sir, raise hand. Sir, is my voice audible to you?
Yes,
sir,
madam.
You may ask your query, Chinay sir. I think it was some technical error. No issue. Thank you so much, ma'am.
Thank you, madam.
Thank you, ma'am. Thank you so much, ma'am. Now, our next participant for paper presentation is Dr. Suhasini Velagapudi, ma'am, with IV Subbareddy sir and Pashunati Manohar sir. Suhasini, ma'am?
Yeah, I'm Suhasini, ma'am. Good morning, one and all. I'm Suhasini from Geetam University, Hyderabad. I'm a research scholar. Presently, I'm working as a lecturer in. One second, ma'am. I'm audible?
Yes, ma'am.
Okay.
Yes, ma'am. You are
working as a lecturer in Falaknama Degree College. My research work is I'm doing with Geetam University. My paper presentation will be also same like Rajashree madam, with a slight difference. I just want to present, ma'am. I'm just sharing the screen.
Yes, ma'am.
Ma'am, I have that directly. I can share, or
yes, ma'am. You can present your screen. In your screen,
but
you can click on the present option.
Present.
Share screen, ma'am.
Share
screen.
Okay, one second, ma'am. Present now. A window. It is not showing on my screen, ma'am. It is not showing share option.
Are you connected with your mobile phone?
No. I'm with my laptop.
Ajay sir?
Because
it
already
is requested to technical team, please help Suhasini ma'am to present the screen.
When I'm presenting,
सर आप देखिए राइट कॉर्नर पे ऑप्शन दिया होगा, प्लीज चेक.
Which one, sir? Right?
या फिर आप एक काम करिए, एक हैंड का सिंबल है, उसके पास में ऑप्शन दिया हुआ है एरो, हैंड के सिंबल के पास.
Shall I send to you, sir? I didn't get you. Present now I can see, sir. So in that it is showing your entire screen, a window and a tab. So
there's an entire screen.
Yes.
पीपीटी आपने ओपन किया हुआ है मैम? सुहासिनी में पीपीटी ओपन किया हुआ आपने?
Yeah, it's open, sir. Already it is on my desktop.
हाँ तो आप शेयर नाउ पे टेब ऑप्शन पे सिलेक्ट कर लीजिए मैम, टेब आप सिलेक्ट कर सकती हैं.
Tab. 1 second, sir. Let me see.
उसमें आपको लिस्ट में कोई पावर पॉइंट का दिखेगा सिंबल.
The share option, it is not showing, sir. That is the thing. Because, sir, what can I do is, shall I forward my PPT to you? Can you present so I can continue my presentation?
So Hasani, you can see entire screen, na?
Yes, sir. Yes, ma'am.
Press on that entire screen. Go to the bottom. You will again see something written there. Like, just tell me what is written at the bottom.
Bottom, it is the share and cancel share option. It is not showing, ma'am.
It's not highlighted, is it?
Yes, yes, yes.
It's not active. Okay.
Mm.
Co-host, you can, I think, Neha, you can make her the co-host.
Yes, ma'am. Yes, ma'am. You, Ajay sir, we can present.
No, ma'am, I will just forward my PPT. You have to present that.
Okay.
Okay. In the meanwhile, continue with other, ma'am. So in the meanwhile, I'll forward my PPT.
Sure, ma'am.
Waste your time. Okay.
I will call next participant.
Okay, I'll call to that person. Okay.
स्वासिनी मैम आप एक बार फिर से डिस्कनेक्ट होकर रिजॉइन कीजिए, मे भी ऑप्शन शो हो वहाँ पर.
Okay, you want me to disconnect, sir?
Yes. Again rejoin.
Yes, ma'am.
Okay, okay, fine.
नेहा मैम नेक्स्ट आप कर लीजिए तब तक.
हाँ, yes, sir. Our next participant for paper presentation is Dr. Noddy sir and King David sir. Dr. Noddy sir and King David sir, are you getting my voice?
Yeah, thank you very much, ma'am.
Yes, sir. You may start your
Thank you.
presentation, sir.
Thank you, ma'am. I'm trying to share my screen. Mango.
Sir, your actually your screen is not visible. Your PPT is not visible.
That's what I intend doing now.
So your screen is visible, but your PPT is not appeared right now.
Yeah, so I don't know. Will someone from the technical department assist me?
You have to start your PPT on your desktop or on your mobile. Your screen is visible.
It's mobile. I'm using my mobile phone.
Yes, sir. Just start your PPT on your mobile. We can see your mobile screen.
Okay. 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 I'm coming. Is it visible now?
Yes, sir. It is visible.
Okay. Thank you very much, madam. Thank you, the organizer. I am Dr. Nodebaga King David, Department of Business Study, Ignatius University of Education, Port Harcourt. We speak on a topic titled Evaluation of Environmental Noise Pollution in an Academic Environment, Port Harcourt. Introduction. A conducive learning environment and education depends on the appropriateness of physical and social environment of classroom. Motivation of teachers and students for teaching and learning, student desire or passion towards learning. The teacher tries to create a perfect environment for learning to the learner in order to prevent information of unnecessary behavior and nuisance, according to Adams 2012. Thus, the learning environment dramatically affects the outcome of academic performance of the student. Looking at that, we are now trying to consider that environment where students are learning, there are some factors or criteria that contributed to the reduction of their grade or poor performance. and looking at that, and noise contributed to that. Then what is noise? Noise is defined as unwanted sounds that hinder an individual's ability towards what they want to hear. These noise are being classified from different sources. We have the external noise derived from traffic noise, maybe the vehicle or motorcycle riding on the road, internal noise, students running in corridors, and also the room noise such as students talking, according to Sept of 2014. Studies have shown that noise has directed negative effect on student learning, with a language and reading development particularly affected. In order to compensate for the noise level in classroom, teachers often have to speak loudly while teaching. Such a speaking habit is known to be a risk factor that may lead to voice disorder in teachers. According to the EPA, noise pollution is defined as unwanted or disturbing sound that reduces your quality of life or disrupt daily activities. Traffic, barking doors, and loud music are qualified, but it's not noise impact usage that matters. Noise pollution, also known as environmental noise, is the propagation of noise with harmful impact on the activity of humans or animals' life. This noise, what are the effects? The effect of noise is generally accepted that noise has a determinant effect for the learning and performance of students. Therefore, the effects are also listed. The noise pollution can also be derived from noise induced by hearing loss. The loss of hearing is not noticeable at first of each one. It's exposed to continuous and medium to loud sounds. Hearing loss as an occupational hazard. We also have the headache and fatigue due to disturbed sleep patterns, hypertension, and cardiovascular disease such as myocardial infarction. The increasing stress leading to psychological disturbance. One may have noticed the degree of annoyance in higher and tolerance is lower in places having loud sound. Types of noise pollution. Where the continuous noise? The continuous noise is what it says on the tin. It is noise that is produced continuously by machinery that keeps the noise without interruption. We also call it intermittent noise. Intermittent noise is a noise level that increases and decreases rapidly. The impulsive noise is most commonly associated with the construction and demolition industry. We also call it industrial noise. It is sound with a high incentive sound are caused by industry machine. Sources of such noise pollution are caused by machine from machinery in various factories and means. This noise pollution is caused by industrial causes, the high incentive of sound produced by machine in various industries, also caused by agricultural machinery. Agricultural machinery like tractors, tube wells, power saw, tractors, power trailers, and harvesters have proved to produce high levels of noise when under operation. We also talk about the household utilities. House utilities are sources of noise that can cause disturbance to the peace of the mind. Common sources of household noise, pollutants include domestic gadgets such as pressure cookers, washing machines, mixer grinders, diesel coolers, etc. The social events like worship places, parties, gifts, and desserts, and so on, create a great deal of noise for the people residing in Port Harcourt. The production of noise, protection from noise pollution. Noise pollution can be protected in the following way. To be aware of the kind of noise around oneself, since it is a subtle form of pollution, it is important to create awareness of it, especially among those living or working in a space like noisy factory, industry, airport, railway, construction site, sports stadium, traffic wardens, mail, etc. Ear protection using ear muff or prop, especially for babies, elderly people, and elderly people, handicapped persons, pet animals, etc. If suspecting hearing loss, get tested. In summary, studies have shown that noise pollution is the main cause of discomfort among teachers and students, which appears in the form of irritability, lack of concentration, drowsiness, fatigue, dispersion, and headache. In conclusion, noise is unwanted sound that judged to be unpleasant, loud, or disruptive to the hearing. From a physics standpoint, noise is indistinguishable from sound, as both are vibrations through a medium such as air or water. Thank you.
Thank you so much, sir. Neeru ma'am?
No questions, but thank you for a good presentation.
Thank you so much, ma'am. Thank you so
Thank
much,
you,
sir.
ma'am. Thank you.
Yes, sir. Please
Thank you,
unshare
ma'am.
your screen. Now, our
Thank you very
next
much.
participant for paper presentation. Suhasini ma'am, are you ready for presentation? Are you here?
Hello?
Yes, Suhasini ma'am.
Yeah, ma'am.
Hello.
Yeah, ma'am. I'm
Yes.
there. I'm there. Let me try once again.
Yes. Nodi sir, please unshare your screen.
Okay, okay. That's what I'm about to do, ma'am.
Can I share, ma'am?
Yes, ma'am. You can share your PPT.
But it is showing that once that Bargran Das remain presenter.
No, ma'am. You can.
Okay. Yeah, ma'am. I got it.
Yes,
I
ma'am.
Okay. I'm happy that my PPT is able to. I can.
Yes, ma'am. It is visible now.
It's visible, no, ma'am.
Yes.
Yeah, ma'am. Let me make it clear. Okay. Yeah, ma'am. Good morning, one and all. I'm Suhasini. Today, my topic is on study of thermopolarizability of ions in lithium niobate open type optical waveguide using point dipole approximation. So my research supervisor is I.V. Subbareddy sir. He is from Department of the Physics, Geetham University. So my main objectives of this point dipole approximation with the open type is the thermopolarizability of ions in lithium niobate used in open type optical waveguide is calculated using point dipole approximation. The refractive index of any material is a function of the local field experienced by the constituent ions. We have used the point dipole approximation and cell near equations to evaluate the variations of ordinary refractive index, that is N0, and extraordinary refractive index Ne, and the birefringence, that is Dn equals to Ne minus N0 in the lithium niobate with the temperature. These values are used to find the possible set of electronic polarizabilities, that is EP, of lithium niobate and oxygen ions at different temperatures from 298 K to 772 K for the wavelengths, that is 0.4545 micrometers, 0.6328 micrometers, and 1.0642 micrometers. The special properties of lithium niobate. This is a unit cell and this is the structure of the lithium niobate crystal. And the main properties are lithium niobate is a well-known ferroelectric material finding applications in nonlinear optics, electro-optics, acousto-optics. Piezoelectric special properties makes it most preferable for photonic, electronic, and sensor applications. And these applications in lithium niobate are large second order optical nonlinearity, wide optical transparency range, high piezoelectricity and photoelasticity, lacing capability, photorefractive effect, pyroelectric property, and high Curie temperature. Strong electro-optic effect. And lithium niobate advantages are it supports a low loss transparency, window covering from visible to mid-infrared wavelength regions. Modern day semiconductor fabrication techniques enhances diffractive index, contrast between the waveguide and substrate, and effectively reduces the size and hence low power consumption, which is a major advantage with traditional lithium niobate devices. This is a lithium niobate waveguide. This is a traditional waveguide. This is a thin film waveguide. Here we can see 1 micrometers and this is a 0.5 micrometers. Here it is a blue color, which is this lithium niobate, and Si is a structure, and SiO2 is the insulating layer. So the study of this presentation is about lithium niobate. Is a uniaxial ferroelectric oxide material with a negative birefringence, that is 0.08, and remarkable optical anisotropy, large spontaneous polarization, electro-optical and non-linear optical activity. All these properties are temperature dependent. In view of this, we have calculated the thermopolarizabilities of the various ions of lithium niobate at different temperatures. We first calculated the polarizabilities of the ions at room temperature using experimental values of refractive indices. Using these values and incorporating the appropriate values of lattice constant at different temperatures, the polarizabilities at different temperatures were calculated using point dipole approximations. The refractive index of any material is a function of the local field experienced by the constituent ions. My next slide is about the expression for refractive indices. Each ion is treated as a point dipole oscillating under the electric field of the electromagnetic radiation. The total field acting at the site of each ion is the sum of the external field and the field due to the oscillating dipoles at the ion. So the relation between the average local field and the average polarization vector is used to define the dielectric constant. So the origin of refractive index in any material is due to the dipole moment of the ions. The dipole moments in turn depend upon the local fields at the sites of the ions. So thus the refractive index can be expressed in terms of the polarizabilities of the constituent ions treated as point dipoles. So these are the mathematical expressions where we have taken, this is a displacement, dipole moment, and these are the local fields. And here, by finding this x, y, z, that are the coordinates which takes place. So x, y, z are the coordinates, and ri is the distance of the point to the origin. So x, y, z, I can find the coordinates of x axis, y axis, and z axis, and I am going to find the distance between the coordinates. Here also the expressions for this mathematical expressions. And going to the next slide about the results. The calculated electronic polarizabilities for various constituent ions of lithium niobate optical waveguide at 6328 angstroms. So this is the electronic polarizability, that is alpha into 10 to the power of minus 24 centimeter cube. These are the values for alpha Li is 0.029, alpha niobate is 1.266562, and oxygen is 2.0044. These are the refractive indices where I have calculated with the experimental, and these are the birefringence calculated and experimental. So I could find the experimental as well as the theoretical, so which is showing the same result. So my next wavelength, that is waveguide, variations of the polarizabilities, refractive indices, and bireference with the temperature lithium niobate at lambda. I have taken 3 different wavelengths. That is, the first one is 4545 micrometers. These are the temperatures with starts from 298 to 772. The polarizabilities of lithium niobate and oxygen. These are the refractive indices where oxygen, that is ordinary and extraordinary rays effects, and this is a birefringence of ordinary and extraordinary, which I get in the negative. So I have taken the 3 different wavelengths, waveguides, that is 6328 micrometers, and one more is 1.0642 micrometers. I can find the refractive indices where ordinary and extraordinary, how the differences it takes place. In my next slide, I can show you in the graph. So this is the refractive index versus temperature at different wavelengths. So I can see the ordinary will be almost ordinary. This is at 4545, and for oxygen, for different wavelengths, that is 4545 and 6328 and 1.0642. For ordinary and extraordinary, I have verified how the ordinary it is taking place and how the extraordinary takes place when the temperature is increased at different wavelengths. So for ordinary, this is the black one for wavelength of 4545, and for this is the green one for ordinary, and one more is blue one. This is ordinary. So red, blue, and this pink are extraordinary rays. So when the temperature increases in the extraordinary rays, it is increasing. So in the birefringence also, I can easily find that birefringence versus temperature at different wavelengths. I can easily find when the temperature is being increased, the wavelength is also being increased. And next is that is about this is about the differences between how the refractive indices versus temperature with the different wavelengths, and this is about the polarizability versus temperature at different wavelengths. So here also I can easily find with the lithium niobate and oxygen, and how this wavelengths of 4545 and 6328 and 1.0642 for ordinary and extraordinary rays, I can easily find when the temperature is increasing how this ordinary and extraordinary ray is affected. How this graph is going to be. This graph shows how I can find it out how this ordinary rays and extraordinary rays I can easily find out. These are the two different wavelengths. So this is a complete picture of point dipole approximation with different wavelengths. And about the conclusion of this paper, as the temperature increases, polarizability of niobate ion decreases and oxygen ion increases for a given wavelength in the case of constant alpha Li. A wavelength increases the polarizabilities of niobate and oxygen decreases for a given temperature in case of constant alpha Li. So the complete work, whatever I have done in this, the work carried out in this paper would help in finding out the phase delay. So ordinary and extraordinary, I can find the phase delay brought out by the material under different temperature conditions. So this complete work I have done by through Department of the Physics, Usmania University, Hyderabad, for providing my experimental facilities. Thank you all. Thank you one. Thank you one and all.
Thank you, ma'am. Neeru, ma'am.
Thank you, Suhasini. That was a good presentation, and I have no questions.
Thank you, ma'am. Thank you so much.
Thank you so much, ma'am.
Thank you.
Now, it is time to call our next participant for the paper presentation, Mr. Mario Verissimo and Horta Lopes. Sir, please, you may start your presentation. Mario Verissimo, sir. Are you getting my voice? It is requested to technical team, please check sir is in the meeting or not. Mario, sir. Okay. Next participant, Nishchal Yadav, sir. Are you here? Nishchal Yadav, sir. P.S. Malviya, sir. And Manpreet Kaur, sir. Are you getting my voice? I think there is some technical error. They are not in our meeting. So, participants whose name is not included in the list, and if they want to present paper, you may present your paper. Okay, I think due to some technical error, our two participants, Nishchal Yadav sir and Mario Verissimo sir, are not here. Paresh sir?
Madam.
Can we continue with the address from our session chair?
Yes, madam. Continue.
Okay, sir. Thank you so much, sir. Now I would like to request Honorable Session Chair Dr. Neeru Bhagat ma'am to address the participants. Niru ma'am?
Yes, thank you so much to all the organizers for organizing such a good session, and thanks to all the participants as well, because I can see the extensive work that everyone has been doing, and it's good to see the young researchers like Suhasini and others to be doing contemporary work, and that is really needed. All these things, like I was already telling one of the participants, Rajshri ma'am, that yes, it is very important for us to do these refractive index studies, because we are going thinner and thinner on our applications and the materials that we are using around us. So that is one part that generally physicists do not look into. We will concentrate on magnetic, optical, everything. Optical, not generally refractive index is what I see that we don't look too much into, but that is really important. So good to see all this kind of research, and more importantly, to see theoretical work going on. It is really, really good. Though I myself am an experimentalist, but I always am in awe of theoretical work that goes on. Thank you so much. And thanks a lot to the organizers for inviting me here.
Thank you so much, ma'am. Thank you so much for your precious guidance and kind words. Thank you so
Thank
much.
you. My
Now it
pleasure.
is time to express our gratitude towards our session chair and all participants and all dignitaries. Today, we have successfully completed our second technical session of 3-day international conference on physics at the world contemporary and innovative application. First of all, I express my gratitude towards our both technical session chair, respected Dr. Uttam Sharma sir and Dr. Neeru Bhagat ma'am, for accepting our invitation and enlightening today's technical session with their presence. Thank you so much, sir and ma'am, for spending your valuable time with us. Thank you so much. I'm
Thank you,
sincerely
madam. Thank
thankful.
you.
I'm
Thank you.
sincerely thankful to all dignitaries who contributed their time, presence, and efforts to make event successful. I may like express our sincere thanks to management of Christian Eminent College Indore and Research Foundation of India for their constant motivation and guidance. It is our proud privilege to associate with Indian Association of Physics Teacher IAPT. I express my sincere thanks and gratitude towards our all respected honorable members of IAPT for wonderful association. I also express our sincere thanks and gratitude towards Dr. Shyama Prasad Mukherjee University, Jharkhand for supporting us, and WFST World Federation of Science and Technology for their sponsorship. Thank you so much from bottom of our heart. My special thanks to our technical team for their technical support. And now finally, whoever gave direct and indirect support, thank you so much everyone. Tomorrow, our technical session will be held on the same time, 11 a.m. onwards. Stay home, stay safe. Thank you so much everyone.
Thank you. Thanks to
Thank
all.
you so much, sir.
Thank
Thank you
you.
so much, ma'am. Thank you so much,
Thank
Neeru
you,
ma'am.
ma'am.
Thank you so much, Prerna ma'am.
Thank you. Thank you, Neha ma'am.
So much. Thank you.
Okay.